Today, we're diving deep, and I mean really deep, right down to the cellular level. We're going to explore the hidden electrical world inside our own bodies that powers, well, everything you do. I mean, really think about that for a second. You decide to snap your fingers, and boom, it happens. How on earth does that signal travel so incredibly fast? It's not magic, it's electricity, but it's not the kind you find in a wall socket. This is something way, way more fascinating. Yup, that's the secret. The key to that speed, to every thought you have, every move you make, is the fact that you have trillions of microscopic biological batteries inside you. Every single one of your cells holds a tiny electrical charge. So let's unpack what this cellular battery actually is. The scientific name for it is membrane potential. And trust me, it's the foundation for absolutely everything we're about to talk about. All it is, really, is a voltage difference. Just like a normal AA battery has a positive end and a negative end, your cells have an electrical difference between the inside and the outside of their wall, or membrane. And get this, it's a specific number. In a typical nerve cell that's just kind of hanging out, not firing a signal, that voltage is about -70 millivolts. That little minus sign is super important. It tells us the inside of the cell is electrically negative compared to the outside. It's charged up and ready to go. But how? How does a living cell build up an electrical charge in the first place? Where does this power come from? Well, the answer lies in how the cell meticulously sorts these tiny charged particles. The real key players here are ions. You've heard of them, right? Sodium, potassium. They're just atoms with a positive or a negative charge. And the cell's whole secret is that it creates this electrical potential by deliberately creating an imbalance of these ions across its membrane. And this slide shows that imbalance perfectly. The cell is working nonstop to keep a ton of potassium ions inside, while at the same time pushing almost all the sodium ions outside. This massive difference is what scientists call an ion gradient. Honestly, this is the best analogy for it. All those separated ions are like a huge amount of water being held back by a dam. The potential energy is just immense. All the cell needs to do to unleash that power is open the gates. Now, you might be thinking, wait a minute, naturally those ions would want to spread out and balance, right? Things in nature move from high concentration to low. So what's stopping them? What kind of machine is powerful enough to build that dam in the first place? Well, meet the absolute hero of our story, the sodium-potassium pump. This is a tiny, incredible molecular machine that sits in the cell membrane, and it uses the cell's own energy to literally force ions to go where they don't want to go, building up that wall of potential energy. Here's the brilliant part. It's the exchange rate. Every time this pump works, it pushes 3 positive sodium ions out of the cell, but it only brings 2 positive potassium ions in. So you do the math. You're losing more positive charges than you're gaining. And that simple, uneven trade is what makes the inside of the cell negative. Okay, so the battery is charged, the dam's full. Now for the exciting part. Let's see how the cell actually unleashes all that stored power to do something useful, like send a lightning-fast signal. This energy isn't just for show. Its entire purpose is to be released in a controlled, incredibly fast burst. That burst creates a traveling electrical signal. And that is exactly how your nerves talk to each other and tell your muscles what to do. And that signal has a pretty cool name, the action potential. It's this dramatic, super fast flip in the cell's voltage that travels down a nerve cell like a wave, carrying a message from one end to the other. And it all happens in a flash, in 2 basic steps. First, bam, special sodium gates fly open, and all that sodium that was piled up outside rushes in, making the inside of the cell suddenly positive. That's the spike. Then, immediately after, other gates open for potassium to rush out, which just as quickly brings the voltage right back down to its negative resting state, ready for the next signal. And this chart just shows you how dramatic that voltage spike really is. The cell goes from its comfy resting state of -70 millivolts all the way up to about +30 and then right back down again, all in just a few milliseconds. That huge rapid swing is the signal. It's the language of your nervous system. So, now that we've seen the nuts and bolts, let's zoom out. Why is this tiny electrical system so unbelievably important? What is it actually powering in our lives? The short answer is just about Everything. I'm talking every single nerve impulse, every muscle you move, every beat of your heart. It all depends on these precise electrical gradients. Your ability to see, to hear, to feel, that's all just changes in membrane potential. It is truly the spark of life. And because it's so fundamental to everything, it also means that when this incredibly fine-tuned electrical balance goes wrong, the problems for our health can be catastrophic. Just look at this comparison. When your ion gradients are healthy and stable, you get a steady heartbeat and sharp, clear nerve signals. But if those gradients, or the pumps that maintain them, are faulty, it can lead directly to some really serious conditions, like heart arrhythmias, or a whole range of neurological disorders. The health of these tiny batteries is directly tied to our overall health. We have covered a lot here, from tiny millivolts to amazing molecular pumps. But if there's one thing, one crucial point you take away from all this, what should it be? It's this: you are electric. Right now, as you're listening to my voice, an invisible, unbelievably complex electrical dance is happening across trillions of your cells. It's a silent, constant storm of ions and voltage spikes that allows you to think, to feel, and to live. It's not just a part of biology, it is the very energy that animates us,